Hey folks, guess what? You made it to the end of your first week of first full week of Physics 111. Nice work. One down, 80 bajillion to go. I know that's exactly what everybody wants to hear, but hey, at least we got this one in the books. Today we are continuing our discussion of linear motion, but there are a few things I wanted to touch base on first, a couple of announcements, things like that. The first is a slight change to my office hours. Now that I've gotten a lot of one-on-ones out of the way, I'm changing the structure of my office hours just a little bit. Starting next Wednesday, my 11 to 12 office hours will no longer accept appointments. They will be walk-in only. You can still log on to Starfish and flag and say, hey, I'm coming in for a walk-in office hour. If you'd like to do that, great. You can give me a heads up. That's wonderful. But starting next Wednesday, 11 to 12 after class on Monday, Wednesday, Friday, that will just be dedicated to walk-ins. My afternoons will remain open for appointments, 1 to 5 p.m. The only difference is that I will no longer have appointments on Thursday. Now that we're into the semester, Thursday is the one day of the week that I'm going to be setting aside to really focus on research and stuff like that. I will have occasional availability, but that will be the exception. So be looking for those appointments Monday, Tuesday, Wednesday, Friday. If you have already made an appointment, don't worry, that's not changing. If you have an appointment already, that's in the books. You can come to it. I didn't cancel anything. But from here on out, my availability is going to change just a teeny little bit. The other thing I want to let you know about was the exam. That is our first exam. Is a Wednesday. I believe it's September 30th. I think, yeah, 30th sounds right in my head. That is a week from next Wednesday. So you got you have exactly 12 days to get prepped for that. Now, I have been receiving some questions because I know folks are a little bit anxious about the exams in general. I will have more answers for you next week. I'm meeting with Dr. Tamaro today. We're ironing out all of the last-minute details, and I hope by Monday to have a really fleshed out idea of what you can expect, and I'll be making an announcement on Brightspace accordingly. If you are attending this lecture from Dr. Tamaro's class and you would like to get notifications from my Brightspace and have access to the lecture slides and so on, you can go ahead and shoot me an email. I'm happy to add you to my Brightspace. The only thing I request is that you specify that you would like to be added to the 111 Brightspace, because I have lots of students from 204 asking as well, and I don't have access to Dr. Tamaro's roster, so it's kind of hard to check which other class that you're in. Just let me know which that you want to be signed up, and I will take care of that. There was another announcement. What was it? Right. I hate doing this one. Sorry. Academic integrity. What that looks like in this class. Thankfully for 111, it's not going to be a huge issue. You have infinite tries on the homework problems, which means you can keep trying till you get it right. There's no risk of trying something new. And we are proctoring the exams, which means you're going to be on camera and we're going to be watching you and we'll be making sure that there's no fishy business going on. But I do understand that there are certain temptations available in the digital virtual space that may be tempting. I addressed this with my 204 class this morning. There are a couple of things that I really support. I really thoroughly support you folks like working together on homework problems and really asking like each other questions and so on. Oh, yeah, actually, brief pause. There was a question in the chat from a student who had asked about the Zoom link to Dr. Tamaro's lectures. I did check with him. The lecture he uses is the same each week. It shouldn't change. And I did go into the syllabus section of Brightspace, and I updated the link in the sort of big list of all of the lecture links. So hopefully that should work. If not, for whatever reason, shoot Dr. Tamaro an email if you want to get in on his lectures. It's just tamaro@uri.edu, and he can, make sure you can get into the lecture. But it is the same one every week, so I'm not sure what's going on there. As I was saying, the academic integrity, this is not a conversation I love to have, but I do know temptation is out there. And I really do encourage you to work together on, like, for example, homework assignments and things like that. Asking each other questions, helping each other get to the right answers. This is particularly true because if it is one of you helping another one of you, then that means the one who's doing the helping has to understand the problem enough to be able to explain it to someone else. And that's actually a really great way to test if you really grasp a topic. Just pick a friend and, like, say, okay, let's divide this chapter in half. You explain the first half to me, and I'll explain the second half to you, and we'll go back and forth. That's a great way of finding the sort of holes in your understanding. Same thing is true of problems. But there is one temptation that I have already caught one student doing. Not in this class, thankfully, because there hasn't been any reason to. But we're only, 10 days into the semester, and I've already flagged an academic integrity violation for this. The one thing that can absolutely not be abided in this class is uploading of any class content to external websites. So these are things like Chegg and Course Hero and stuff like that. This is particularly true from the exams. If we manage to find anything like that, there is a zero tolerance policy. You get a 0 on that assignment, it cannot be dropped, it cannot be made up, and you are immediately referred to the Academic Integrity Office. And I know that there is this idea that, oh, it's anonymous, we all have the same assignment, it's not a big deal, I can't be caught. But I want you to be aware that websites like Chegg and Course Hero and all of the rest of these, they actually are more than willing to work with universities, and if we flag an exam, we can find out who put it up there. So please, do not risk that. It is a terrible consequence if you end up getting caught doing that, and the reward that comes from it is probably not worth it. Because if you take advantage of all of the other resources we have, Dr. Tamaro and I will bend over backwards to make sure you get the best shot at understanding physics as possible. The TAs in the help lab will make sure you get the best understanding of physics as possible. We'll do everything short of just finishing your assignments for you. We'll pull you across the finish line if we have to. But that last bit has to be you, and we can't have you exporting any of your work to other websites. So I'm saying this up front. Be aware that we not only know about it, we are actively policing it, and the consequences are dire if you get caught. Take advantage of the many resources you have at your disposal. Don't give in to the temptation to use the ones you don't. Hopefully it won't be an issue. We're doing proctoring, so hopefully everything will be fine, and I won't have to have this awkward conversation with anyone from this class or Dr. Tamaro's. But again, I've already had the conversation once this semester, and we're in our lecture 5. So please, 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 let's all be a happy family together. Something of note, my 204 class has actually made a class Discord so they can collaborate and work together and stuff like that. Totally in support of this. Big thumbs up. And so if you'd like the same sort of thing, we can arrange that for Physics 111. Just let me know and shoot me an email, and we can get something sorted out for that, for those of you who might be interested. Okay, now I think that's all of the doom and gloom out of the way. Back to regular old energetic Professor Coyne at 10:08 a.m. as his phone is absolutely exploding in his pockets with emails. Whew. Okay, today we are continuing our discussion of linear motion. This is the summary slide from the end of last class. No, where are you going? Come back. There we go. I'm just going to leave it up here for a second as I give the little spiel so you can kind of take in the quantities that we're going to be dealing with today. Last class, we spent some time trying to understand these things graphically, and today we're going to try to spend some time understanding these concepts mathematically and mapping how they connect to one another in sort of actual mathematical parlance. To that end, we're moving on to the topic of motion in one dimension. So we're going to do some practical examples using constant acceleration. First, we'll handle left-right acceleration. That's like a car accelerating from a stop sign to get up to highway speed. And then we'll do up-down, the up-down direction, which is free fall and the force and the acceleration due to gravity. Now, to that end, we're going to have to define some variables to go along with all of these concepts that we have. And that's what I've done here. We use these variables to describe specific quantities. And for one-dimensional motion, the really important quantities are these: how much time has elapsed, an object's initial position, its final position, its initial velocity, its final velocity, and its acceleration. And we use these symbols over here to represent them. T is elapsed time. X is an example of a variable we would use for initial position. We usually use X when it's horizontal and Y when it's vertical. That's just a convention because of the XY coordinate plane. There is an initial velocity, V sub 0. You'll often hear this referred to as V naught. That just indicates the naught meaning 0. And 0 meaning the velocity at time equals 0. So when you start your stopwatch, what is its initial velocity? V is the object's final velocity, and A is the object's acceleration. Now, these 6 variables are related to one another with 3 different equations written here. These equations describe kinematics. Kinematics is the study of motion. And so these are the physical the physical equations that we use to relate velocity and time, position and velocity, and acceleration, and so on. Now, in some textbooks, and in fact some of you may have seen this in high school if you took physics, there's often actually a 4th equation included here. I don't include that because it is just a different variation of these. You can mix and match. You can play with these using algebra. You can solve for a variable here and plug it in here, vice versa. In fact, that's a very common approach. What you'll often see in problems is maybe you solve this equation for time, then you take the result of that solution and you plug it into this equation to find position. We're going to start getting into situations where there are more and more multi-step problems. We're going to try to develop a way of training ourselves to think about them so they can be solved. Now, it's worth noting that each of these equations has different variables in it. And the book provides a very nice table that I reproduce here. Each one of these equations depends on different variables. And so the variables that you have and the variables that you are interested in can dictate, sorry, just a little notational typo, the variables that you have and the variables that you need can dictate which equation you use. For example, if you need x, the final position, well, you can't use this equation because x doesn't appear there. Similarly, if you want the final velocity, well, look, there's a big hole. This equation doesn't have final velocity in it, so you can't use this one for that. Similarly, if you need time, you can't use this equation because time doesn't appear there. Now, I do want to mention, just real briefly, that these equations up here can sometimes be represented in slightly different ways. So you'll actually see the variables that we use to represent the different quantities change a little bit. The equations themselves will always be the same, but we'll often use subscripts to indicate that we're talking about a specific direction. If you note down here, I mentioned that, for example, we might use x when we're talking about horizontal and y when we're talking about vertical, but then we might also use v naught x to indicate the initial velocity in the x direction, and ax to indicate the velocity, the acceleration in the x direction. That is actually the answer to the question that was just posted in the chat, which is what was the x doing in this equation. I fixed this one and this one, but I forgot to fix this one. So sometimes you'll see this top equation written as, say, vx equals v naught plus axt. Sometimes you'll see vy equals v naught y plus ayt. These are the same equations. We're just making little annotations with these subscripts to indicate that it is in either the x or the y direction. Similarly, down here, you might see this written as y equals y naught plus v naught yt plus 1/2 ayt squared when we're doing a problem that involves vertical motion. So just keep that in mind as we're going through. Now, with that said, there is a sort of algorithm that you should follow whenever you're approaching problems involving kinematics. First, and I cannot stress this enough, draw something. You don't have to be a good artist. Sketch something down, relative positions, all of that stuff. Label everything. A really good example of a problem that is can be very hard, but can be vastly simplified by drawing a picture is that, I think it's problem 5 from the homework, where you have John, I think, rollerblading down a road towards a mailbox. Now, in that particular case, it's, there's a mailbox a meter in front of him, what's his position, and draw the position versus time plot. I had probably a half-dozen meetings with students who wanted to talk about that problem this week, and it was almost invariably solved by the fact that if we drew that out on a number line, where the mailbox is set at x equals 0, 1 meter, 2 meter, 3 meters in front in the positive direction, and then 1 meter, 2 meters, 3 meters in the negative direction, just drawing this number line and indicating that, well, John is the mailbox is in front of John, so John must be behind the mailbox, which puts John here to begin with, looking all proud of himself, and then indicating that because in that problem, John is moving with a negative velocity to begin with, that allows you to kind of conceptualize, oh, okay, well, I know he's going to be moving this way, so at t equals 2, he has to be over here somewhere, and we can calculate what that is. Then his velocity changes to 0, so John stops, so his position isn't going to change. Then John starts moving forward with a certain velocity, and so he's going to end up over here. This picture proved critical to helping folks understand that. So I can't stress enough. Draw a sketch, label everything you can possibly label. It might help you conceptualize what the problem is asking for. Once you have drawn your sketch and labeled everything, make sure you make a note of which variables you know and which ones you don't, meaning which ones were you given values for, which ones were you not given values for, and importantly, which one do you need? Like, what is the question asking for? Once you know that, you can find the equation that relates your knowns and your unknowns. God. It's a good thing I'm not an English professor. You find the equation that relates your knowns and unknowns. Once you are here, then almost everything just becomes a process of algebra. Solving the unknown equation. Now, in this class, one of the sort of challenges that I think many of you will run into is that I do all of my algebra symbolically, meaning I manipulate the variables, and then at the very end, I plug in values. Many of you will instead be used to plugging in values and then doing algebra. I encourage you, if you can, to resist that temptation. If you do the algebra symbolically, it is 1,000 times easier to diagnose what went wrong when you don't get the correct answer. Because particularly if you come to me, I can look at an equation and be like, oh, like this line of the equation is right, but this one is wrong, and here is the algebra mistake that was made when everything is written in terms of variables. If you had plugged in those things and you just like sort of wrote them down and combined the numbers and just kind of did algebra, it is impossible to distinguish an algebraic error, dividing when you should have multiplied, adding when you should have subtracted, that kind of thing, from calculator errors, plugging something into your calculator wrong. Those problems can be so hard to diagnose. And because the last step here is to do sanity checks, I encourage you to try to adopt the algebra first, enter values later, because part of the sanity check that you want to do in the end is double checking that you did the algebra right. Now, one other thing I want to mention is this last point here. Keep in mind, every now and then, your equations will spit out two answers. This usually comes from taking a square root, because whenever you take the square... That was a weird sound. Whenever you take the square root of something, you end up with a plus or minus in front of it, on either positive or negative value. You, in those cases, need to choose whichever answer best fits the situation. Sometimes it makes sense for an object to have a negative velocity. Sometimes it doesn't. You need to use your physical intuition to tell you which is which. Now, with that said, basically, we're just going to do practice problems for the rest of the class, more or less. I'll do a little bit of talking in between, but yeah, we're just going to do some practice problems. Hooray. So, in part, there. As part of a stunt routine, we have a car. It's moving backwards at a certain speed, at which point the driver shifts into forward and slams on the gas pedal, creating a constant forward acceleration. What is the velocity 4.61 seconds later? This indicates that the forward direction is positive. So the first step, like I said, is always going to be to draw a picture. So, you know, everyone can have a different style of how they want to do these things. And here we got a little poorly drawn car. And there's my little sketch. Got a car driving along. And we are told that forward is positive. So I'm just going to label the positive and negative sides. Here we go. Now, I'm also told some information about what happens here. I'm told that the car is initially moving backwards. So this is where it starts. So this is its initial velocity. And that is 16.6 meters per second. Note that I forgot to update my slides down here, my little cheat sheet. This is the fourth kinematic equation that I was talking about that we can actually kind of ignore. It's never really all that relevant. I just neglected to remove it from the slides. I apologize. If it's useful to you, it's available. You can write it down. You can use it. It's fine. It's completely correct. We just usually don't need it. Sorry for that confusion. Anyway, we have the initial velocity. We know that it's backwards, so it's pointing towards the negative direction. We know its magnitude, 16.6, and we know that it is the initial because that's what it's starting off at. Now, after the initial situation, the driver shifts into forward and slams on the gas pedal, creating a constant forward acceleration of 5.74 meters per second. So I'm just going to write A over here, indicating that it is forward to the right, and so that it is 5.74 meters per second squared. And the only other thing that we're given is that we want to know what the velocity is after 4.61 seconds. So here is where our game of identifying knowns and unknowns come in. We are given three values, which means we know what the initial position is, we know what the acceleration is, and we know what the time is. So I actually come down here and I just check off the variables that we know. Then, what I always do is I come to the problem, I see what it's asking for. Here it is the velocity after 4.61 seconds, and I circle it. So I know that this is what I'm looking for. And at this point, I can do my first pass. I look at my kinematics equations and I say, well, which ones of these can I use? Well, I'm looking for v, so my equation should have v in it. This one has v, this one has v. I can use either of those. This one, however, does not have v, so I just cross that out. I know that equation is not going to be useful for this problem. So then I come back over here and I try to narrow this down. It's sometimes helpful to indicate that I can't use equations with variables that I don't know. So I get rid of any equation that depends on x or x naught. Well, that leaves me here because this one has position in it. I don't know anything about the position, so I can't use that one either. And so by simple process of elimination, I conclude that this is the equation that I should use. Now, once I have that, like I said, it becomes algebra. V equals V naught plus AT. Well, hey, look here. I don't actually need to do any algebra. This equation is already giving me what I'm looking for, V. So now I can actually just go in and plug everything in. Now, the first very important thing is when I'm plugging in values, positive or negative is important. The velocity is pointing to the left, so the velocity is negative. That's what's being indicated over here. Its magnitude is 16.6, and its direction is to the left. So because this is one-dimensional motion, my velocity is, is negative 16.6 meters per second. That is plus my acceleration, which is positive 5.74 meters per second squared, times time, which is positive 4.61 seconds. Note that I've done a couple of things here. One, I've enclosed all of my numbers in parentheses. This is just a sort of way that I use to really kind of wrap my head around like signs, like positive and negative. When I plug in a negative value, that goes inside the parentheses. This is in contrast to an equation. Sorry, folks. I accidentally fat-fingered the stream button when I changed my camera, so I stopped the stream, and I'm just letting sure it catches back up. Sorry about that. You saw a little jump there. That was my mistake. What I was saying is that the positive sign is from the equation, but the negative sign that is in the parentheses comes from plugging in my value. And that's just a way to keep things organized. Now, once I have all of that, it just becomes a matter of plugging it into the calculator. I get negative 16.6 plus 5.74 times 4.61. Remember, when you're plugging into your calculator, be unambiguous. Make sure things are doing what you expect them to. And when you do all of that, I think we get something like 9.86 meters per second. The other thing that you'll notice that I did is I plugged in the units. And that's because units are algebraic things too. Seconds here cancels with one of the factors from seconds here. And you can see that I get meters per second as my units. This is a way of sanity checking. When you reflect, your units should be consistent. That's the dimensional analysis we covered in Chapter 1. And also, numerical values should be reasonable. And so there are a couple of things there. Does it make sense that he now has a speed of about 10 meters per second? Well, sure. The speed was originally 16, so 10 seems reasonable. The second question would be, does the direction make sense? This is positive, and this was negative. Well, does that make sense? That we're going to have to rely on our physical intuition. Imagine you're in a car, backing up, and then you slam on the gas, and you stay on the gas for 4 seconds. Well, almost 5 seconds, actually. In that particular case, you start squilling out. Yeah, it totally makes sense that you could start going in the opposite direction if your car is accelerating fast enough. So this answer probably checks out. So I might submit it on, Sapling for the homework and be like, yeah, good, correct, or no, it's wrong. Well, okay, I did my sanity checks. I know I did my signs right. I know my units work out. Well, maybe I just made a calculator error, and then I try my new thing and so on. Of course, not all problems are this straightforward. There's a question in the chat, since the car is moving backwards, isn't V naught 16.6 meters per second with a negative sign out front? Yes, that is what's indicated here because the arrow is what's giving the direction and this is the magnitude. If it makes more sense for you to write it down just with the negative sign to begin with, that's totally fine, but you'll note that that is in fact what I plugged in over here. Okay, Unfortunately, not all problems are as straightforward as this one. Here we have a police car that's parked on the side of the road. A speeding car passes by, at which time the police car accelerates to catch up to them while the car continues at the same speed. We have two questions we want to answer here. How long does it take for the police car to catch the speeding car, and what is the distance of the chase? Now, this is a scenario where what's happening is the car is speeding along at a constant speed. When it gets here, the police car starts to accelerate. But it starts slow. It takes some time for it to get up to speed where it can finally catch up to the speeding car. So we're actually going to break this down in a couple of parts. First, we'll do how long it takes the police car to catch up. Now, I've already gone through the process of labeling all of my values here. I'm being very careful. I'm noting which ones are positive and which ones are negative. In this case, they're all positive. And I'm also labeling the initial position and the final position. First, you'll note that this never specified the initial position. If that's the case, you can usually assign a position of x equals 0 just to make it more convenient. Once you have the initial position set, and this is broadly a convention, you could set it at something else if you wanted, we will want to indicate where the final position is. At what point does the police car finally catch up? I'll note that this is an abstract thing. This is just a line that I've labeled x. I don't know what the value of x is, but I know there will be a point somewhere down the line where the two cars finally do catch up to one another. And I'm just indicating that here so I know that that variable is going to be x. This is an abstract concept. This is not obvious. So it might make sense that I'm saying it now, but if you were to have this homework assignment, this may not be clear. So please do keep in mind that I am filling in information that is implicitly given instead of explicitly given. That's a challenging thing that you're going to have to practice before it starts to feel natural. And so if you have trouble with that, these are the sort of setup things that I can help nudge you on when we talk about, when you come to office hours. So now that I have everything labeled, the car is not accelerating and is traveling at a constant speed. The police car starts at rest and accelerates at a constant rate. Now I can come down to my kinematics. And once again, I'm going to go ahead and get rid of this. Sorry for the confusion. All right. So how long does it take the police car to catch up? We know that's going to be time. Well, great. Except we have two cars. Which one is x? Like, which one do we use for which variables? And herein lies the first problem. We actually have two sets of variables. Why do you keep slipping away, buddy? There we go. We have the values for the police car, and we have the variables for the speeding car. Sorry, wrong button. Note that I'm doing that thing I said before, where I'm labeling my variables with a subscript. I now have two sets of variables, and I know different things for the different cars involved. I know both of their starting positions. They start here at x equals 0. I know that they end up at the same position, so these are going to be equal. I know both of those. Well, actually, I don't know those, but I do know that they're going to be equal. I know the initial velocity for the police car, which is 0. I know the initial velocity for the speeding car, which is 0. I do not know the final velocity of the police car. And theoretically, I don't know what the final velocity of the speeding car is either. except I know what its acceleration is, so I know its final velocity has to be equal to its initial velocity. But that's theoretically something we are not given. And finally, I know what the acceleration of the police car is. Note, however, that I only wrote time once. I didn't include it in this column. And that's because the time is actually going to be the same for both cases. They are not two different times. There's a person right here with a stopwatch that clicks the stopwatch, and when the police car catches up, they click the stopwatch again. And time is the variable that allows us to go back and forth pretty quickly. So let's take this and see if we can evaluate any of the information here about which equations that we can use. We know that we have no information about the final position. It's just a variable at this point. So we can't use any equations that have a final position in it. So that one's a final position. That one has a final position. And so we're only left with one equation. Well, okay, let's see if we can use this equation to get our result. Well, if we look at the speeding car, if we were to write this down for just the speeding car, it's Vs equals V naught S plus AST, except the problem here is the acceleration of the sports car is 0. So this whole term is going to go away, and I'm just left with that my final velocity is equal to my initial velocity. Okay, that is informative, but it's not useful. We want to solve for time after all. What about for the police car? Vp equals V naught P plus APT. If I look here, it has the variable we want. It has the acceleration, which is given. It has the initial velocity, which is given. It's 0. So that term's going to go away, which is good. And then it just depends on the final velocity. But wait a minute. I don't know what the final velocity is. I can't solve this equation either. If you were doing this at home on the homework, what you'd run into, none of these equations give you the final answer. You just can't do it. This would be a common sticking point. This is an example of a multi-step problem. We need to use something about this problem to give us our first step so we can solve for t. And these problems are by far the most challenging in this course. And so I'll tell you how to do this here, but it's not going to be like this for every problem. Every problem is a little bit different, and it's stuff like this that really makes physics hard. So if you're having trouble with this kind of like multi-step thing, don't hesitate, make an appointment, come to my office hours, we can talk about it. Now what we're going to want to do in this case is start over and note this important statement I made right here. We know that xs is equal to xp, meaning the two of them stop at the same place. So that is actually going to be my starting point. Now, xs and xp are both included in this equation and this equation. So these are our two options. That one doesn't have x in it, so it doesn't use this piece of information. This one does. But note, this equation also includes the final velocity, which we don't know for the police car. So that's not going to be immediately useful either. If we look down here, though, we know the acceleration for both. We know the initial velocity for both. We know the initial position for both. So we can use this equation here. And what we do is we say the final position, for example, for the police car, will be equal to the initial position of the police car plus the initial velocity of the police car times t plus the 1/2 acceleration of the police car times t squared. So that's going to be the right-hand side. And similarly, The left-hand side is going to be the same thing, but for the speeding car instead. The final position is the initial position of the speeding car, the initial velocity of the speeding car times t, and 1/2 AST squared. Now at this point, we can do some simplification. And the one exception to plugging in numbers early is 0. I recommend as soon as you can identify a term that is 0, get rid of it, because that will simplify the algebra a little bit. For example, we know that the initial position of the speeding car is equal to 0. We know the initial position of the police car is also equal to 0. We know that the acceleration of the speeding car is equal to 0. And we know that the initial velocity of the police car is equal to 0. So if I plug in those zeros, we see my equation gets much, much, much simpler. V naught speeding car times t equals 1/2 a police car t squared. I'm solving for time, so I will divide both sides by time, and what that's going to do is it's going to cancel out this one here. It'll cancel out one factor from here. I am then going to multiply both sides by 2. That will cancel this out, and I will divide both sides by AP. And I get, that will cancel this out, that my time is going to be equal to twice the initial velocity of the car divided by the acceleration of the police car. Now I can plug in my values. 2 times initial velocity of the speeding car, 15.8, divided by the acceleration of the police car, 4.36, and that should give me a time of t equals about 7.25 seconds. There's the answer. At this point, we can then move on to the next part of this problem, which is to find the distance. But now the difference is I know what the time is, so I can go back and say, for example, solve for any number of these, using the variables, because I now know what the time is. For example, I could just use this equation again for either of the cars, and that will give me the final result. But since we have a little bit more to get through, I'm not going to go through that on the slides. I encourage you to try that at home, and if you run into any trouble, come talk to me during office hours. All right, the last thing I want to talk about is what happens when we move from horizontal to vertical. And that is a special type of motion that we call free fall. That is to say, it is the motion that occurs when the driving force behind the acceleration we experience is gravity. Now, free fall is a very special type of motion, so I want to spend a little bit of time talking about it before we do a practice problem. Now, any two objects that have mass will attract each other with a force that we call gravity. In our day-to-day lives, we're used to the gravity as the thing that keeps us on the surface of the Earth. The Earth pulls down on us, and we can walk around and live happy-ish lives. I don't know, 2020 is kind of a dumpster fire, so maybe we're not happy right now. But certainly gravity is what allows us to stay here on Earth. But actually, any two objects with mass attract each other with gravity. This is a laser pointer. This is a lens cap for my camera. These two pull on each other with a force due to gravity. Problem is, these things are really small. The force due to gravity is negligible between them. You know what is not small? The Earth. The Earth is big, like pretty stupid big. It has a ton of mass. And so for large objects like planets, moons, stars, things like that, gravity is not negligible, and that's why we experience it so clearly. Now, objects that are near the Earth's are constantly pulled down by Earth's gravity. No matter where you are on the surface, it always gets pulled straight down to the ground. Now, during this motion, we can say if Earth's gravity is the only thing pushing or pulling on the object, we say the object is in a state of free fall. So, for example, this is free fall. But if I just lower this gently, it is not, because my hand is also pushing or pulling on the object. Now, actually, that not really free fall either, not perfectly, for reasons we'll get into shortly. But I do want to mention that it's a close enough approximation. Now, whenever something is in free fall, they experience a very specific acceleration. This acceleration is so uniform that we give it a special symbol. Lowercase g is the acceleration due to gravity. And it is so ubiquitous in physics that it gets its own symbol. Now, all objects fall at this rate, no matter what their mass is. And to prove that to you, I'm actually going to see if I can turn up the volume a little bit on this thing that I'm playing in the background. And I'm going to play you a video. So I'm going to drop off, and I'm going to let you watch this for a couple of seconds. Hopefully it will, actually, you know what, I'll describe what's happening here instead of letting our host do it, because I think I have a more engaging speaking voice. So what they're doing is, this is a huge silo that NASA developed to allow, it's a big vacuum chamber. So this is a big area that they can suck all the air out of. And what they're doing is they're raising up a bowling ball and a bunch of feathers, and they're going to drop them. And as one would expect, the bowling ball falls straight down, and the feathers just very lightly float down to the ground. This is exactly consistent with our day-to-day life. And this is because the difference in the objects play into how the physics work here. Now, you might be tempted to believe this is because the bowling ball weighs more than the feathers, but that is not the case. It's something else. And to prove that, what we're going to do is we're going to close this chamber. These big rooms are going to, this big door is going to swing closed, and it's going to seal, and then it's going to pump all of the air out of that room, and we're going to repeat the experiment. Now, I'd like to indicate here that the feathers are very, very light. They have very little mass, and the bowling ball is quite heavy. Now, just watch what happens when they repeat the experiment after all of the air has been sucked out of the room. This is something that may or may not surprise you depending on how familiar you are with physics. So, okay, here we go. They're lining it up, they're getting ready, and wait for it. Press the button. You know you want to press the button. Give it a moment. There we go. And here we go. We're watching it in slow motion. Watch as these two things fall at precisely the same rate. Without air in that chamber, there is nothing pushing back on these objects. And so they are truly in free fall. And objects in free fall always accelerate at the same rate regardless of their mass. So the feathers in the bowling ball actually hit the ground at the same time. Pretty crazy, right? That's not what we expect from our intuition. Now, this discovery is credited to Galileo, but actually, it's a lot older than that. Galileo famously did experiments in the 17th century, but in the 6th century AD by Philoponus, who was a philosopher at the time, he actually made that same observation, that the rate of fall really doesn't depend on the masses. And if there is a difference in time, it's very small. You can try this at home by dropping, say, a bowling ball. Well, I mean, you'd have to have a bowling ball. But you can try this at home by dropping a bowling ball and a golf ball. Air resistance doesn't affect those very much, so they'll fall at the same rate. Now, it was finally Galileo in the 17th century that really tried to understand why this is the case, and he was the one who took the first steps towards understanding that it was air resistance that made, for example, feathers fall much more slowly. And again, I can give you a classic example of that. Here's a paper. It's one of the lecture notes from my 204 class, so you can see it's got a couple of nice blue bars here. And I'm just going to let that fall. Yeah, nice and slow, right? Well, all I need to do is take that same piece of paper, see, same blue bars, crumple that up to minimize its surface area, and when I drop it, straight down. In fact, it will fall at the same rate, more or less, as my laser pointer. So air resistance is the reason that light things appear to fall slower. But in actuality, what's happening is those lighter objects are not actually in free fall. They have two things affecting them: gravity pulling them down and air resistance trying to slow them down. For this class, when we talk about free fall, we are ignoring the effects of air resistance, because it turns out that stuff is very complicated. And when you ignore the effects of air resistance, all objects are going to have the same magnitude of their acceleration. We turn that into a vector by saying that up is usually positive, down is usually negative, and so our acceleration for our kinematics equations will be equal to negative g. So acceleration is negative 9.8 meters per second squared. Now let's do one example of this. That's all we have time for. There are a couple more examples in the slides. I'm happy to work through those in office hours if you want to come by. But let's just do the one here. Now, for our purposes, the process is no different than before. It's just that the direction is different. I'm going to get rid of this semi-useless kinematic equation, and we'll go through the same process we did before. Now, the only trick about free fall problems is that you are notice in that image that's over there to the left, and notice in the problem statement, there is no mention of what the acceleration is. We are given the initial velocity. We have Megan is a pitcher on a fast pitch softball team, and she clocks her fastest pitch at 29.7 meters per second, and she throws it straight up, and we want to know how high the ball would go. Well, we know if we throw something up in the air, what's going to happen is it slows down and eventually comes to a stop and then falls back down. Well, we're interested in knowing how high is it when it comes to a stop. So we know the final velocity is 0. We are told the initial position, 1.6 meters. That's where Megan releases the ball from. And ultimately, we want to know the height. So we want to know what x is. So note, we are not given any information about t. So that rules out this equation and this equation. Our only option left is this one. But you'll notice this depends on a, and a isn't stated anywhere. That's because this is a free fall problem, and we can assume the acceleration in a free fall problem is, and always will be, on Earth, negative 9.80 meters per second squared. That gives us the last piece of information that we need. So now we have our equation, v squared equals v naught squared plus 2a x minus x naught. This is an example where I need to solve for x, and I'm going to do that symbolically. The first thing I'm going to do is I'm going to subtract v naught from both sides. This has the effect of moving v naught over to the other side of the equation. I'm then going to divide both sides by 2a, which gets rid of that coefficient. And then I'm going to add x naught to both sides. And that will give me my final answer. Now, I can make this process a little bit more streamlined by noting that the final velocity is 0, which means this term is going to go away, which means that my final result will actually just be negative v naught squared over 2a plus the initial position. And now here, we have to be very careful when we plug things in. You might be tempted to just plug this in and be, well, hey, wait a minute, this is a negative number, and it's going to be big. This is a positive number, it's going to be small. Wouldn't this give us a negative result? But acceleration here is negative 9.8. So we have to plug negative 9.8 in down here. This I'm going to get out of the way real quick, and I'm going to rewrite this just a little bit over so I have room. Negative v naught squared divided by 2a plus x naught equals negative, plug in for v naught, 29.7 meters per second. That's squared. That is divided by 2 times the acceleration, negative 9.80 meters per second squared, plus my initial position, 1.60 meters. And note that when I take care of all of this stuff, we'll see things like the negative cancels with the negative. Seconds squared and seconds squared. Meters will cancel out with one of the meters. All my units will work out. And when I plug this into my calculator, hold on a moment, 29.7 squared divided by 2 times 9.8, and then add to that 1.6, I get something like 46.6 meters, which is, of course, the final answer. So please keep in mind that free fall problems always let you assume what the acceleration in the vertical direction is. Of course, that doesn't prevent free fall problems from being hard. This one is quite challenging. What happens if you drop a penny off the Empire State Building? You know, that classic problem, will it split somebody's skull? The answer is no. But if it falls down, you know, how long will it take for the penny to reach a position of 124 meters? So now the initial position is 369 and the final position is 124. You have to plug those in for x and x naught. Similarly, what if instead of somebody throwing a ball up, Billy shoots something straight down with a slingshot? That's going to change your initial velocity and your final position. These are all things that can complicate the problem, but unfortunately we don't have time for. So with that said, we are done for the day. We are going to wrap it up right here. If I have a meeting with you later this afternoon, I will see you then. Otherwise, I'll post an update on Brightspace with a little more information once I have it regarding things like the exam and what study materials we'll be providing you. And if I don't hear from you folks, please have a great weekend. Enjoy a little bit of rest and reprieve after what was no doubt a very long and very stressful week. Have a good one, folks. See you next Monday.